My name is Yogesh Wadadekar, and I'm an astronomer at the National Center for Radio Astrophysics. And the topic of my talk today is how to do astronomy using archival data. The nature of this topic is somewhat different from the other lectures that you've been receiving so far. So the focus of my talk is going to be mostly informational. There are going to be a lot of hyperlinks that I will provide on the different slides, and that will help you sort of access more information or access more data as the case may be. So let's get started. So first of all, we need to ask ourselves the question, why is using archival data an important component of astronomy research today? And the reason for that is that astronomy is now drowning under a deluge of data. For the last many years, the growth of publicly available data in astronomy has been exponential, with a doubling time scale of only a few years. And like any exponential, as we have seen recently during the pandemic, uh, in the early stages, you don't notice it too much, but suddenly it dawns upon you that this is something big. And that has happened to astronomy over the last decade or so, wherein the availability of wide availability of data has completely changed the sociology of astronomy. When I started doing research 2.5 years ago, these were the sort of steps that one took. One thought of a research problem, and one then identified a sample from existing catalogs that would help answer the research problem. Then one identified a suitable telescope that would give you data of sufficient quality and quantity in order to answer your scientific questions. And one submitted an observing proposal. Now, typically, observing proposals are submitted every 6 months or so. And so after submitting, you wait till you get the time. If your proposal is rejected, which it may well be the first time it's submitted, especially when the telescope is highly oversubscribed, you simply have to wait for the next cycle and resubmit your improved proposal. Then hopefully get observing time. Then you travel to the telescope and you made your observations. This The last step, of course, was not possible if you were using a space-based facility, but most ground-based facilities required you to travel to the telescope or have someone else observe on your behalf in order to get your data. And then if the data were good, you would then reduce and analyze. If the data were bad, you would probably need to submit an observing proposal again. And this whole process, from thinking of a problem, identifying samples, writing proposals, and so on, and getting your data would take 1 year at a minimum, okay, and very often longer. So these kind of things were okay on PhD's time scales, but it was very difficult to do research if you wanted to do something on very short time scales, like for a summer project. Now, with the wide availability of data, the problem can be posed as follows. You think of your research problem as before, you create a sample as before, but instead of going to a telescope, you go to an archive wherein you search for data. And very often you will find not just raw data, but also data in a scientifically usable form, so-called reduced data, which you can simply download and analyze. And the quantity and quality of public data today is much larger than it was, say, 2 decades ago. So the sociology is completely changed. But there are some caveats that you have to remember. Okay. One thing is, if the data are public, that means if you have access, then everybody else in the world with a fast internet connection has the same access as you. They could think of the same research problem, they could download the same data, do the same analysis that you propose to do, and publish sooner. So you could easily get scooped. So you have to be careful. So you have to define your problem carefully. You have to identify the data sets that you want to use carefully. And then once you do that, you have to work as rapidly as possible in order to get your scientific results. Another thing that one should remember is that when you are handling your own data set right from scratch, you will be intimately familiar with the caveats or the limitations or the problems that exist in a particular data set. If you have simply downloaded the data, then you have to be much more careful. You have to do many more quality checks. Fortunately, many of these large surveys have their own fairly intensive, fairly detailed quality control checks. And they do inform you about the quality of the data, usually via some flags which point to problems with the data. So you are absolutely, when working with catalogs, images, or spectra, must make absolutely sure to look at the flags, the error flags, and ensure that the data that you're using are not damaged in any way, so that the scientific results that you will derive from the archival data are robust. So if you keep these two things in mind, I think there is a lot of work that can be done with archival data, but these caveats must be remembered at all times. Astronomical archives are an old idea. Okay, I think the first archive of astronomical data took the form of a star catalog that was constructed by the Greek astronomer and mathematician Hipparchus about 2000 years ago. And he basically made a catalog of stars that he could see in the sky and tried to get their positions and so on. And therefore, he's also considered the father of astrometry, which is the measurement of positions of various celestial objects. Tycho Brahe, many years later, just before Kepler, came in and he carefully measured positions, but this time he measured the positions of the naked eye planets relative to the fixed stars in the background. And of course, he didn't have a telescope, but nevertheless, his observations are some of the best observations made before the advent of the telescope. His observations were particularly important because a few years later, Johannes Kepler used Tycho's observations in order to derive his laws of planetary motion, which all of you must be familiar with. And this, of course, needless to say, changed the course of astronomy, if not all of science. So archives have an old history. In the early years, the archives took the form of catalogs of various objects. So for example, in 1603, Bayer published his catalog of stars. We still use some of the Bayer designations of stars for some of the brighter objects, brighter stars in the sky. In 1771, in France, Charles Messier compiled a catalog of nebulous objects. These objects were objects that were likely to be confused with comets by people who were hunting for comets. And therefore, he made that catalog. And those of you who are amateur astronomers are surely familiar with the Messier catalog, which is more than 200 years old. By the 1800s, the study of galaxies had taken off, and Dreyer compiled something known as the New General Catalog, NGC, in 1888 with more than 7,000 objects. So as you can see, that working with catalogs is not a new idea, but what we really would like to do is look at data which is richer. And one of the ways you can look at richer data is to look at images of the sky. And in the 1950s, a very large survey of the sky was carried out with this telescope. This is the 48-inch Schmidt telescope at Palomar Observatory. And the gentleman you see standing in front is Edwin Hubble, who discovered the expansion of the universe. And the Palomar Observatory Sky Survey carried out in the 1950s provided us with the first photographic map of the heavens. Remember that until that time, there had been, of course, a lot of individual photographs that had been taken of specific objects, but there was no large area survey. And this particular telescope was specially designed to have a very wide field of view so that it could image large parts of the sky at one go and produce this survey for us. Some years later, another similar telescope was used to carry out a survey of the southern sky. And with that, for the first time, we actually had a map of the entire sky in visible light in the form of images. Technology has played an important role in the growth of archives. And the main advantage that technology has brought is the ability to carry out new digital surveys of the sky, but also the ability to scan older photographic plates using this kind of machines. It's referred to as an APM machine, which was used to scan the photographic plates and made available to us initially in the form of CD-ROMs, which were widely distributed to astronomical observatories in the 1990s, and later on now, of course, using the internet. Digital observations are, of course, much better than these digitized plates, and this figure illustrates for you why that is the case. The curve at the top is for what is referred to as a back-thinned CCD, and you can see that the quantum efficiency of that varies between, say, about 40% to about 80-90% over a fairly wide range of the visible waveband, from about 400 nanometers to 800 nanometers. And this is an order of magnitude better than photographic plates, which only achieved about a 10% efficiency, quantum efficiency of detecting photons. And because of this, there has been, without increasing the size of the telescope, at least for optical telescopes, we were able to increase the efficiency of the telescope for astronomical observations. There is one more advantage that digital brings, is that the calibration of digital data is far easier than the calibration of analog data, because CCDs, for example, have a very linear response. So which means that if you double the time of your exposure, you expect to receive, say, double the number of photons, right, from your astronomical source. And the counts that you get out of the CCD are also double. So if you calibrate it at once, you calibrate for your object and identify the number of counts that correspond to some flux from your source, you can look at other objects in the field and so on, and get their calibrated fluxes quite easily. So I just mentioned CCD technology developments, but there have been parallel developments in other wavebands also. For example, if you look at radio interferometers, which you have been introduced to in the last 2 weeks, the development of optical fiber signal transport, the development of software correlators that allow you to correlate the data coming in from the different dishes of the GMRT, for example, and developments in low noise amplifiers and other electronics have enabled orders of magnitude growth in both the quality and quantity of astronomical data. So technology really, particularly electronics and optics, have played a very important role in the growth of astronomical archives. The other major development, of course, is the growth of computing. Those of us who are old enough to have seen some slow computers truly appreciate the speed with which modern computers work. And this, of course, is the famous Moore's law, which leads to a doubling of transistors on the integrated circuit chips after a period of time, typically 18 months or so. And after that, because of that, within a space of 30-40 years, there has been a very dramatic improvement in the computing capability. This improvement in computing, I've just shown you the increase in number of transistors, but there has of course been a corresponding increase in the amount of storage that we have on our computers, the amount of RAM that we have on our computers, and the speed with which we can connect to the internet. So these two threads of developments in digital electronics and CAD/CAM technologies for fabrication of electronics and optics related to astronomy, and accompanied with these parallel developments in computing technology, have led to a manifold increase, and the widespread access to the internet with a vast increase in net speeds has made these vast data sets very easily accessible to a larger community. This has also enabled science that could not have been imagined some years ago. So there is a new area of science called citizen science, where astronomers and other scientists employ the services of volunteer citizens to help them analyze their data. And this is the picture that you see on your screen is from some project known as Galaxy Zoo, which basically shows you pictures from a modern survey called the Sloan Digital Sky Survey, and asks you to classify galaxies as smooth or with features and a disk and so on, and shows you galaxy after galaxy and compiles statistics from many thousands or many hundreds of thousands of users across the world, working out of their own interest and without any monetary remuneration in order to help classify galaxies. So this is, of course, just one. Galaxy Zoo is just one of the many citizen science projects that are running in astronomy today. And although astronomy pioneered it, other scientists, biologists, for example, are also using now citizen science in order to improve their analysis of data, which is sitting in large archives. When you have these large archives, you need to develop software tools for accessing the archive. Okay. And why are software tools necessary? Because we are asking questions like, how do we find out what data are available? And how do we search for data in these very large archives? Once we have a large data set, how do we visualize it? How do we combine multiple pieces of information in different locations, which means in different archives? There may be a radio archive and an optical archive. How do you combine data from the two in order to carry out your analysis? And so the question is, are there a common set of software tools that we can use for all these activities? It turns out that we do, and I'll now mention the most widely used tools very briefly. I must point out that there are more specialized software tools that I'm not going to mention today, but I'm sure that if you start doing research with archives, you will quickly be able to find and use those tools. So the simplest tool that one needs is access to research publications in order to find out what work has already been done in the research area that you propose to work on. And this has probably been mentioned already. There is something known as the NASA ADS, and you have the link up here, which is a digital library which maintains bibliographic databases from more than 14 million records, and has basically links to papers in astronomy, astrophysics, physics, and the archive e-prints. And there is also a similar website called archive.org, which provides open access to more recent papers in many different fields, as you can see here. And of course, there are mirrors of the ADS site all over the world. So this allows you to search by topic, by research area, by title of the paper, by objects, by authors, and so on. The next step is catalogs. Okay, so as we saw, since we astronomers have been making catalogs of objects containing information for a very long time, since the time of Hipparchus. Now, in addition to catalogs that are compiled by various people historically, many modern papers, the kind of papers that you will find in the ADS, will contain catalogs which need to be accessed electronically for further analysis. And this is made possible through a website called Vizier. There's a mirror of Vizier in Ayuka, so I've given the link to that, but the original site is in France. And there are query tools in Vizier that allow the user to select relevant data tables and to extract and format records matching given criteria. So if you're looking, let's say, at a catalog of galaxies and you're interested in objects that are brighter than a certain optical magnitude, you can specify that in the query tool in Vizier and only select those objects. And more than 10,000 catalogs are available in Vizier, and they can be downloaded in a variety of formats. The third tool that one should look at is something known as Topcat. And Topcat is a piece of software that allows you to visualize catalogs. So what are catalogs? Catalogs are basically tabular data. There are rows and columns. The rows typically contain all the different objects in the catalogs, and the columns contain the parameters that have been measured, the physical parameters that have been measured for each of those objects. Topcat is a very flexible tool. It understands a number of different astronomically important formats. FITS, VO table, and CDF are some that come to mind. It offers a variety of ways to analyze tables. You can browse through the data themselves. There are good facilities for visualization, for calculating statistics, like the mean, median, mode, the standard deviation, and so on. You're also able to combine tables together. So there are flexible matching algorithms available for you to, let's say, positionally match, let's say, a radio catalog with an optical catalog in order to find, for example, the optical counterparts of radio sources. It has its own Java-based expression language. Okay, the language is useful so that you don't have to do everything interactively. Once you know what you want to do, you can write a short program that will match catalogs, for example, or make plots, histograms, and scatter plots, and so on. The data themselves can be edited, and the modified table can be written out in a wide variety of formats. It works well without any network connection, but it is tightly integrated to something known as the virtual observatory, which I'll talk about in a minute. Using virtual observatory protocols, Topcat is able to cooperate with other tools, services, and data sets in the VO world and beyond. So it is possible for you to load your catalog and match it with another catalog which is not sitting on your computer, but is sitting on some remote server which you access through the internet using Topcat. Topcat has been written in Java, and therefore it runs happily on all different operating systems that we use today. So this is for accessing catalogs. Now, for accessing images, the most popular tool is something known as Aladdin. Aladdin is basically an interactive sky atlas that allows you to visualize images, and you can visualize your own images that you have on your computer. Or again, if you're connected to the internet, you can visualize data from all sky surveys. You can superimpose entries from astronomical catalogs or databases and interactively access related data and information from other databases online. So you can go to an object in Aladdin, and you just hold the pointer over the object, and if you hold it for a few seconds, it automatically goes and queries some databases like the Simbad database, which is a database mostly focused on stars, but also now includes many other things, the Vizier catalogs, and other archives for astronomical objects in the field. So very, very powerful tool. You should explore it. It has excellent user manual also available and freely available for download at the website that I'd given at the top. Aladdin is also written in Java, and therefore it works quite smoothly on all operating systems. It is possible to combine Aladdin and Topcat with a tool known as SAMP. SAMP is actually a protocol. It's a messaging protocol that allows information exchange between uh, VO compliant tools, virtual observatory tools. So what you can do is you can load a catalog in Topcat and then send the catalog to Aladdin via SAMP. So you open your image in Aladdin. So let's say you have a radio catalog and you have an optical image. You can load the catalog in Topcat, load the optical image in Aladdin, and then send the catalog over from Topcat to Aladdin so that you can then see what are the objects, where your radio sources lie, what the optical counterparts look like, and so on. Very, very useful. You can also do the reverse in Aladdin. If you want to select a few objects, okay, you can select them and then you can create a table based on those objects and then send the table back to Aladdin, back to Topcat, and then visualize the measurements for the objects that you have marked. DS9 is another possible, another popular piece of software. It's an alternative to Aladdin. It's a tool for looking at images. It provides many of the features that Aladdin provides. It has a fast, lightweight interface. It is also nicely integrated with the virtual observatory. And again, using SAMP, you can communicate with Topcat. So you can send a catalog from Topcat to DS9 and so on. So we've mentioned this term a few times so far. It's called the virtual observatory. So what is this all about? As the growth of astronomical data sets became very, very large, and it became clear that in order to do the best science or scientific research with the available data, one should be able to combine data sets and different data sets sitting in different places into a seamless whole. This was done via an international collaborative project known as the Virtual Observatory, and it's being coordinated now by an organization called the International Virtual Observatory Alliance, or the IVOA. And what the IVOA does is that it debates and agrees to technical standards that are needed to make the VO possible. So in most cases, the most important thing that you need to do is to define standards for information exchange and ensure that all the tools that use that standard actually conform to that standard. And that is the job of the IVOA. It also acts as a forum for discussing and sharing VO ideas and technology, and a body for promoting and publicizing the VO. So the tools that we have looked at, Topcat, Aladdin, etc., were developed by the VO community. India was one of the pioneers in the VO effort and has developed some tools like VO Plot, Virtual Observatory Plotting software, which are widely used within the VO community. So for example, when you use Topcat or Aladdin and so on and try to make plots, the code that they use underneath is the VO Plot tool that was developed by the Virtual Observatory India. So there are a few concepts that you need to understand when you start working with data in the virtual observatory. The first, of course, concept is FITS, which you may have encountered. FITS is short for the Flexible Image Transport System. It's now the standard format for astronomical images, tables, even spectra. And it specifies a standard way of expressing metadata in keyword value pairs, has a few number of mandatory keywords, which have to have a particular meaning if a file uses them. Okay. Then in order to query astronomical data, a new data language was developed, which is called ADQL, Astronomy Data Query Language. The format of this language is very similar to one of a language called SQL, Standard Query Language, which is used for accessing data in sitting in databases. So ADQL can be thought of as an enhanced version of SQL that allows you to run queries within some astronomical context. So for example, in SQL, you wouldn't be able to run a query like show me all objects within 10 arc minutes of this position, okay, on the sky. And but with ADQL, you can do that. There are special functions available that allow you to search, uh, to run a search on a database using some concept that is only there in astronomy. Cone search is what is enabled by the availability of ADQL. It's a simple data service that allows you to ask a query like, show me all objects in the catalog which are within a given radius of this specified location in the sky. Okay. This, of course, is called a cone search because in 3-dimensional, this is basically the radius will define for you a cone in space. And you get a fixed set of column back set by the data service in question. So you get all the objects that correspond, that lie within a certain radius of a specified location. This is for getting a catalog back. If you want to get images back, there is something known as a simple image access protocol, which returns astronomical images within a certain position and radius, within a certain distance of a specified positions. You can get cutouts of a specified size or a fixed size image from an atlas of images and so on. There is a similar protocol called the Simple Spectrum Access Protocol, which works for astronomical spectra. VO table is a standard format for tabular data within the VO. So most data archives now offer the option of exporting data in VO table format, and a large number of tools like Topcat, for example, happily read VO tables, and any FITS table can be expressed as a VO table. So there are tools to translate between the two. There is something known as TAP, which is called the Table Access Protocol. Okay. So where a cone search allows you to search only by sky positions, the TAP service allows you to make searches along the lines, give me all the records with B minus V, that's a magnitude in the B and V band is greater than 0, and give me just columns B, D, F, and G, and so on. So you can really customize things much better than you can with a simple cone search. Okay, so now that we're familiar with commonly used terms in the VO world, let us look at what are the major astronomical archives that exist. So in the optical, there are many archives. I've listed 4 large archives here, and highlighted in bold is the Sloan Digital Sky Survey, which I will talk about in a little more detail in a few minutes. In the radio, of course, again, there are many archives. I've highlighted the GMRT Online Archive because that is something that we run. I'll point to certain interesting science that can be done with the data in that archive as well. In the X-ray, you have, again, 2 large archives, one from the Chandra Space Telescope and another for the XMM Newton Space Telescope. And you must remember that I've only listed the really, really large data archives here. In addition to these, there are many other archives and also hundreds of websites that serve data to the public, typically releases from large surveys. Okay, we'll look at the Sloan Digital Sky Survey in a minute to see how a well-designed archive works and how it allows you to access data in a variety of ways. So a large archive of radio data is the archive of the Giant Meter Wave Radio Telescope, the GMRT Data Archive. So GMRT, as you would have all learned, is operated by the NCRA, and we have archived all interferometric data gathered by the telescope since the first public cycle in 2002. Okay, these data now are over 200 terabytes, and are currently being served to registered users using a modern search interface as part of the NCRA Archive and Proposal Handling System, NAPS. Here's the URL. And the GMRT archive is the largest publicly accessible astronomical data archive at the moment. We are only serving raw interferometric visibilities so far, but over the last year or so, we've been processing some of the old data that is sitting in the GMRT archive and generating process continuum images and releasing them through the NAPS system. So we've released more than 4,000 images so far, and mostly observing cycles between 20 and 30 are the ones that you'll find data for. And the goal behind this exercise is to provide some value added data that should make GMRT data easier to use for non-experts. So instead of having to put in the large effort involved in taking the raw data and processing it through to get the science ready continuum images, we are providing the science ready continuum images directly to the users. So I'm just going to flash a few pictures of data that have been released or will be soon released as part of the GMRT archive processing project. And here's one example of a pair of supernova remnants. The background image was constructed from the TUMAS survey, which is a near infrared survey. And in the foreground, you see these two large circular blobs, which are supernova remnants in the disk of the Milky Way. Then there are, of course, many radio galaxies that have been observed with GMRT over the years. And here's an image of one giant radio galaxy, again processed by us through the data in the archive. And the background image is from Pan-STARRS, and the foreground image is from the GMRT. Another kind of science is looking for relics in galaxy clusters. So this is a very famous relic known as the armchair relic. The background image is this time from the Hubble Space Telescope. It's an high-band image from Hubble. And in the foreground is the GMRT image. And you can readily see why this relic is referred to as the armchair relic. It looks like an armchair. And so the purpose of showing these few images to you was to just highlight the fact that now it's become, with modern astronomical archives, it becomes easier and easier for users to download the data and use it directly. You should be careful about the caveat that I mentioned previously. How was the data processed? Okay. So in order to help the user, we provide a complete log file with many thousands of lines long, which specifies exactly how the data was processed. We also give users access to the exact version number of the software that was used to, software pipeline that was used to process the data, and so on. So if users want to, they can actually verify that the processing that we have done does not introduce any problems for the kind of analysis that they want to do. GMRT also carried out a very large survey known as the TGSS, TFR GMRT Sky Survey. It basically used up about 2,000 hours of GMRT time at 150 megahertz about a decade ago and gathered a lot of data. This survey covers more than 99% of the radio sky north of minus 53-degree declination, and it covers 3.6 pi steradians. Okay, so very large fraction, 90% of the full sky has actually been observed. And a radio source catalog containing positions, flux densities, and more for 0.62 million sources down to a 7 sigma peak to noise threshold is now available. It's available in the form of what is called as the ADR1, Alternative Data Release 1. And the data processing and the various data products are available in this paper. This paper has now nearly 400 citations, indicating that it's been quite a success, and the data from the TGSS are being used for a wide variety of scientific analysis. The data products are available in the form of the ADR image archive. There is also an image cutout service, and there is also a source catalog of the entire all the objects that have been detected in the survey. It is important to mention here that this TGSS ADR data release is also fully integrated with the virtual observatory. So you can use virtual observatory tools in order to download and analyze the reduced TGSS data. I also wanted to mention something known as the Sloan Digital Sky Survey, which is a digital survey of the entire sky. What you see here on the left is the Palomar Observatory sky survey, the digitized sky survey with the APM plates. And on the right is the same part of the sky with the Sloan Digital Sky Survey. And you can readily see that both the sensitivity and the resolution of the SDSS is far superior to what you get with the photographic plates. And this is a survey that aims to cover 1/4 of the sky, pi steradian, using a custom designed telescope. There's near simultaneous imaging in 5 optical filters with follow-up spectroscopy of more than 1 million galaxies and more than 1 lakh quasars. And the original goal was to study the large-scale structure of the SDSS. Why is this special? This survey is special because the largest freely available homogeneous data set of imaging and spectroscopy in the sky. The quality of the data and data processing are excellent. Many data products are available, ranging from raw images and spectra to final catalogs of measured parameters. It's unlikely that an effort on this scale will be attempted in the next few decades, so it could be around for a long time, particularly the spectroscopic component of the Sloan. The data sets are precisely defined and free. Other researchers can easily reproduce your results. And this is very important, this idea of provenance, wherein you specify exactly how a scientific result was obtained so that others can reproduce it and verify that you haven't made some basic mistake. And the survey has been going on since 2000, so more than 20 years, in several different iterations. Currently, the SDSS 4 is about to end, and SDSS 5 is about to start. And with every iteration, which runs for several years, they make some improvements and they change some of the parameters and introduce new instrumentation for the survey. It's been a very successful survey, more than 8,000 papers, more than 4 lakh citations, with a very high H index. Although it was originally designed for studying the large-scale structure of the universe, it has made enormous advances in scientific areas, like in the study of asteroids, Kuiper belt objects, dwarf stars, etc., which were not originally envisaged. Its data are available to collaboration members immediately and to the public in the form of a public data release. There was an early data release and was followed by data release 1 through 16, approximately 1 data release every year. And data release 16 was released in 2019. Okay, so there are many, many objects. So just to give you a feel for that, it covers 14,000 square degrees now because it's the expanded covering area. And there are 469 million unique objects that have been detected in the SDSS. And spectra include 2.8 million galaxies, 960,000 quasars, and more than 1 million stars. And these numbers, for those of you who have seen the evolution with time, will find these numbers to be quite staggering, because early on in my career, for example, when I started working on AGN, there were only about 10,000 quasars known. Now there are 960,000. So it's been a dramatic increase in the numbers. The practices for data access and distribution were adopted as best practices by the entire community. Okay. And of course, you must remember, you must look at the caveats, the biases, the limitations, and the SDSS provides an extensive set of quality flags to help you understand the limitations of particular data sets, so that you can understand the limitations when you start analyzing the data. The data can be accessed in various ways. So just like we saw for the TGSS, there is going to be access to the spectra and image mosaics via something known as the Science Archive server. And there's something called Sky Server, which provides you simple browser-based access to the various catalogs. CAS Jobs is an advanced SQL interface for querying the imaging and the spectroscopic catalogs. There are also numerous tools to explore individual objects, images, spectra simultaneously, generate finding charts, and so on. So, as I mentioned earlier, these are the sort of now the standard best practices for providing access to large surveys in all of astronomy. So far we've looked at accessing data in the archives by searching for individual objects or visualizing things in Topcat, Aladdin, and so on. But how do you work if you want to access archives programmatically? And why is this important? This is important because when you're dealing with samples of 1,000,000 objects, you cannot afford to look at each object individually and figure out what's going on. You need to do it as part of a computer program. So in order to do that, the most popular language that is used is a language called Python. I'm sure most of you have heard about Python. Some of you probably already use it. If you want to do astronomy and data analysis, Python has become an indispensable tool. It's very, very popular. It's very easy to learn. It's a complete ecosystem. If you learn Python, you practically don't need to learn anything else. At the bottom here is a link to a course on Python for astronomical data analysis that I co-taught with Kaustubh Wagmare. You can go and look at the link. It'll be an easy way for you to learn Python. Python usage in optical astronomy is very wide, and a large number of tools and softwares in astronomy use Python in optical astronomy. In radio astronomy, the dominant tool nowadays is something known as CasaPy, which is a Python interface to the APES++ data analysis system for radio astronomy. It's the default system for analysis of JVLA and ALMA. It also works very well with GMRT data. There is also a Python interface via something known as parcel tongue, which allows you to call APES tasks from within a Python program, and so on. And there are many others which are listed here. And most of the new developments are happening in the Python language. If you want to use Python for astronomy, then the most important tools are listed here. You need to use something called NumPy, which allows for fast array processing, a module called SciPy, which provides a number of modules for scientific computing, a plotting tool called matplotlib. It's the standard plotting library for Python. And for astronomers, one of the most important packages is called AstroPy, which contains a set of core packages and dozens of affiliated packages that operate well within the AstroPy environment. You may also want to use AstroQuery, which provides tools for querying online data sources. So a little more details of what AstroPy allows you to do. Okay, it allows you to work with different astronomical coordinate systems, different units and quantities that are specific for astronomy. It allows you to read and write various kinds of files. It allows you to do cosmological calculations and image processing operations like convolution and filtering. It allows you to visualize data. There are also some tools for astrostatistics. Then of course there are the nut and bolts which allow you to interface nicely with the underlying Python package. So last but not the least is AstroQuery, which is an AstroPy affiliated package that contains a collection of tools that allow you to access astronomical data. Okay. And each web service has its own sub package. What means is that you have, suppose you want to access the SDSS, you will use one sub package. If you want to access the VLA archive, you will access another sub package, and so on. And through AstroQuery, you can search and download data, be it catalogs, images, spectra, from many large surveys through a Python program, okay, that you will write. So taken together, AstroPy and AstroQuery are very, very popular Python modules that will allow you to access data and really open yourself to the vast world of astronomical data archives. So I'm going to stop here and take your questions and comments. Thank you.
So you described how Python is the most used language and like most useful by now. Uh,
Yes.
was in contact with some people who are actually working in the field and like working in some field, and they said Fortran is more preferred.
For what? Not for data analysis, I hope.
I'm not sure. They said that
Okay.
if you want to be an astronomer, like
Huh.
you want to work with astronomical data, Fortran is more preferred nowadays. So that I was a bit confused when you mentioned that, okay, I would focus on Python or Fortran.
Yeah, no. So Fortran is still being widely used for example, for numerical simulations and things like that. Okay, where there is a large body of legacy code. Okay, so code that has already been written in Fortran for the last 30, 40 years, and therefore you don't want to throw it away in order to write something new. But the advantage of Python, even for that, so before we go there, I must say categorically that this statement is not true if you're doing data analysis. If you want to do data analysis, then Fortran is not very useful at all. Okay, in fact, it doesn't have any good visualization tools. Forget more sophisticated things. So nobody uses Fortran when they're working with data. A lot of people use Fortran when they're working with numerical simulations of various kinds, and that is because of the legacy software that's available. Now, even for that, Python has an advantage there, because what Python can do is that it can easily interface with a Fortran program. So what it means is you write a Python program that runs a Fortran program in the background, calls a Fortran program, and even exchanges data. So if that Fortran program creates an array of outputs, you can transfer those arrays into Python and then use Python to plot the data and so on, where Python tools are really quite sophisticated. So even for numerical work, people are using Fortran now for the heavy lifting, because Fortran is runs faster than Python does, and therefore you use that for all your numerical simulation work. But for the analysis, visualization, etc., you do that in Python.
All right, sir. Thank you.
Excuse me, I'd like to second the answer. Since I'm a computer scientist, and here in our physics department, people really use Python. So Python is really useful tool when you are dealing with visualizations. And sometimes they do use other languages as well, but mostly Python for data analysis. Like it's really hard to do data analysis with language that does not provide you with tools that you can plot easily graphs and simulations. So we use a lot of Python and VPython, which is a specific package on Python that allows us to simulate physics components and situations. So I just like to second.
Okay, thank you. Thank you for your comment.
Hello, sir.
Yes, please go ahead.
Yes, sir. First of all, thank you for providing such great information, sir. It was really wonderful. Sir, I had a question that we were given some experiments in the school, sir. So we had to perform certain points to get the information. So every data set has to be like that in hierarchy, or there are any a number of indexes to follow to get information from data sets got from astronomical data. So I wanted to ask that.
Yes, let me try to understand exactly what you're asking. What do you mean by indexes and so on?
Indexes in the means chronology. You have to follow a certain chronology for means first we have to derive this, then this, then this. Is there any format for that,
It
or we
depends
can?
on the science problem that you are trying to address. So every scientific research area has its own sort of process and procedure. And as far as the data sets are concerned, they're really very diverse. So what is typically there with every data set that you download, there is something what is referred to as metadata, which is the description of the data. So for example, if I give you a table with columns and rows, I have to tell you what each column contains. Is that the flux? Is that a flux? Is that the luminosity or something else? I also have to tell you what the units are. So is the flux in Jansky? Is it in millijansky or something else?
Yeah.
Okay. So that metadata is very important, and that is there with every data set that you download. There will be a description of what data is there, and that helps you in your analysis. I mean, that's absolutely crucial. Forget helping, it's absolutely crucial in your analysis.
Yes, sir, yes. Okay, thank you, sir. Thank you very much.
Yeah.
Sir, can you just tell that how can we use Python to use VO tools, virtual observatory tools in the interface?
Yes. So Python allows you to use the virtual observatory tools through the Python program. Okay. So you will import. Are you familiar with Python?
Yes, sir, a bit.
Huh. So what you will do is you will download the Python Virtual Observatory module, okay, or the AstroPy module, and you will install it on your computer, and then you will start your Python interpreter, and you will do import AstroPy, and then you will use AstroPy dot all the functions that are available within AstroPy in order to query databases. So you don't have to worry about making a connection, which database to connect to, and so on. All that is nicely coded already into the Python package. So you will have to, so every package comes with its own API, the application programming interface. That is the API provides you with certain functions that allow you to access data. And that data may be in the form of catalogs, it may be images, spectra, or something else.
So we can access the data online, means we don't have to have a local copy or something.
You don't have to have a local copy necessarily. You can even access two catalogs online, okay, search through them and only download the response to the query. So for example, if I know that in the STSS there is a catalog of quasars and I'm only interested in quasars at redshift greater than 6, I can run a query in my Python program which gets transmitted to the server, and that query runs as a SQL query on the server, and that generates a list of quasars at redshift greater than 6, and only those quasars are sent back to me, and then they arrive into my Python program as an array, and then I can match that array with some other let's say an optical catalog or radio catalog or whatever it is, in order to gather more information. And all of that can be done without having a local copy of the software. In fact, it's becoming increasingly uncommon to have a local copy, primarily because of the size of the things. Like if you want to download a local copy of all the Sloan Digital Sky Survey, that will be many hundreds of terabytes. Okay, you will not be able to store it. And the query will be run very slowly if you try to run it locally on such a large data. So yes, absolutely, you can run things remotely on the server side.